Next reaction, addition of X2 to alkenes. Remember, X is chlorine, bromine, or iodine. All right, fluorine doesn't do any of these reactions, so we just kind of ignore fluorine. What you might want to start doing is start making a list of these reactions. So on a separate piece of paper, write reaction 1, the first reaction we learned, which was the addition of HX to a double bond. And actually write out the reaction and any special rules, like Markovnikov's rule. Second reaction was the hydration and the hydroboration, and any rules that were, all different about that. The hydroboration reaction is the anti-Markovnikov. I don't remember if I used that term or not, but that reaction is called hydroboration because you're adding a boron to it and a hydrogen. And then your next reaction is going to be the addition of X2. And it's exactly as it sounds. Notice in every reaction we're starting with a double bond. So all we're doing is changing our electrophile each time. That's all we're doing. Our nucleophile is the same. Our nucleophile is a double bond. It's just that we just keep changing our electrophile. All right? And what happens is you get a halogen on both of your carbons. And what we're going to learn is that you do get what's called a trans addition or an anti-addition. It's actually called an anti-addition, and it gives you the trans product. Now, when you do not have a restricted bond, then it rotates, and technically you can't tell it's trans, okay? But the mechanism is an anti-addition mechanism, all right, which means that your X's, your bromines, are trans of one another. Now, in a single bond, this is free to rotate, so it doesn't really show up as trans, but in the mechanism, it goes through a trans mechanism. And I'll show you an example. Remember, ringed compounds have restricted rotations. So if you take a double bond and add Br2 to it, what you get is bromine on each side, but one of the bromines is up and the other bromine is down. All right, so you get the trans product. All right, this is trans, and the reason is because in the mechanism it goes anti. So let's see why. Okay, so we have our double bond. Let's do it on the cyclohexene. We add it to Br2. All right, the pi bond grabs the bromine, bromine leaves. Now in this case, we do not form a carbocation. This is important because a lot of people think you form a carbocation, but you do not. What you form is what's called a halonium ion. Halonium. I'm not making this up. That is really what it's called. In this particular case, it's called a bromonium because it's a bromine. Bromonium ion. All right, halonium implying a halogen ion. All right, bromonium and bromine. If you had a chlorine, chloronium. If you had an iodine, iodium. Okay, again, you can't make this stuff up. That's really what it's called. Okay, so you do not form a carbocation. No carbocation. Okay, you form the positive charge on your halogen, and you form this three-membered ring. All right, we've learned three-membered rings are strained. So imagine you got a big bromine in there on top of it. This snake really wants to break. Okay, so what's going to happen is your bromonium ion, all right, is pretty strained. Your other bromine, all right, remember this bromine has 7 lone pairs, is going to come in the opposite side of where your bromine is, okay, to form. So this is the anti-addition part of it. Anti-addition. And I'll show you in 3 dimensions on the next page. But that bromine is coming the opposite side. So let's say these bromines are coming out. Let's say that's coming out. You have a bromine, and then your other bromine came from the opposite side of it. Okay, let's look at a side view of this. 3-dimensional view. So here's your bromonium ion. Okay, it's puckered up. Your other bromine comes from the bottom. Let's get those. I realize you probably can't see dots on this, so let me. So this bromine has to come in from the bottom, and it breaks this bond, and then this bromine just kind of moves over. All right, so your final product is you got this bromine up and this bromine down, hence the trans product. That's why you get trans. This is how they proved, because what they found was that whenever they did this reaction, they always got the trans product. They never got any of the cis product. So this part of it is what's called the anti-addition. It's adding opposite of where the other group is. All right. If it was an anti-addition, if the bromine could attack from the top, they wouldn't even call it anti-addition. Right? Anti just means that every single time this goes, 100% of the time, the halogen always adds opposite of where that bromine is. Okay? That is the trans product. That is a halogenation reaction. All right, the next reaction we're going to talk about is the addition of hydrogen. Right? This is called hydrogenation. All right, you've probably heard of hydrogenation, like partially hydrogenated compounds. But hydrogenation means you take a pi bond and you add hydrogen across it. Again, your pi bond is the nucleophile, your hydrogen is the electrophile. You can use a catalyst. This uses a catalyst. It uses a platinum catalyst. Your book likes to use platinum oxide. So it's PtO2, platinum oxide. You can also use something called palladium on carbon. This is how they write it. So it's palladium, Pd, and it's on carbon. They might also use platinum on carbon. All right, depends on how much money you have. If you can afford palladium or if you can afford the platinum, really doesn't matter. Okay, basically you hydrogenate and you get rid of the double bond. This is what's meant by saturated. You know how they say saturated? We learned about saturated. This is what saturated means. You're saturating your molecule with the maximum number of hydrogens. Maximum number of hydrogens. You can't saturate anymore. You can't add any more hydrogen to it. You've saturated it. That's where the name comes from. And this is a cis addition. Okay, we're going to kind of look at the mechanism. It's really not that too exciting. But basically, the cis addition implies what happens is the platinum is a solid. All right, so imagine I have a piece of platinum. What happens is the hydrogen absorbs onto the platinum. All right, and your double bond, let's say here's your double bond, it kind of lost room here, but our double bond approaches the platinum with the hydrogen, so the hydrogen adds on the same side, since the platinum is kind of bound onto this. There is no anti-addition. This is a cis addition, okay? So if you have, let's say you have this compound, double bond with two methyl groups, and you add hydrogen with platinum oxide, sorry about losing room here, what's going to happen is the hydrogen is going to add on the same side, pushing the methyl groups on the same side. So your final product is going to look like this. You'll have a methyl group, and a methyl group are going to become cis because your hydrogens are both on the back side, or on the same side. All right, so your compounds always come out as cis, and that is hydrogenation.